Yeah.
Okay. Earlier we talked about the pump is one component of a system. Okay? So the pump is attached to the inlet line. And what are some things that could be found on the inlet line of a system going into a pump? This is where you talk back to.
A valve.
A valve. Pressure gauges. How about a turn, a 90, or a pipe fitting, right? Have you ever seen a basket strainer or filter in an inlet line? Okay, this particular system doesn't have one of those, but those are things that could be on an inlet line, right? We have the feed tank. Now for this system, the feed tank and the discharge tank is the same because it just cycles through. So here's the feed tank coming inside, into the tank, into the pump, all right? This is what we looked at upstairs. The pump is connected to a coupling that is connected to the motor, okay? And on the discharge side of the pump, what are some things that you'll find on the discharge lines or discharge side of the pump? More valves, turns, right? Pressure gauges. How about a flow gauge or flow meter? Okay? All right, now how do we start a pump? Remember how we start a pump? We're going to open it up, we're going to flood, we're going to prime it. Okay? So, we're going to pump about 45 gallons per minute right now. Now remember which one we're maintaining that imbalance. What's greater, this side or this side? The pump. The net positive suction head that is available has to be greater. Okay. Now, all is well in the pump system. This gauge here is reading, none of you are going to come up, are you? Come on up here and read this gauge. Seriously. It's reading 0. Okay, on the inlet it's reading 0. On the discharge it is reading 14 pounds. This over here tells us the kilowatts or the amps being used. What is it, about 1.20?
Yes.
Okay. Life is good in the pump system. I am going to simulate an obstruction on the inlet line. Okay? Let's say a basket strainer becomes partially restricted. Does that ever happen? Yeah, okay. So I'm going to close this valve off to simulate a restriction on the inlet side of the system. What's going to happen to this inlet gauge? Is it going to go up, stay the same, or go down? I saw one up. So everybody's going to go with the one thumbs up? Oh, Chip. Carrying the weight of the world on your shoulder. Here we go. All right, now, the discharge gauge. Is the pressure going to go up, stay the same, or down? Well, Chip, you have some people with you. I see more down. All right. What's going to happen over here, excuse me, with the amps? Are the amps going to go up, down, or stay the same? Chip's giving me the thumbs up back there. Who agrees with him? Everybody shake your hands. Losers. All right, here we go. Is that your final answer? No, no, no. Here we go. Now, the first thing that's going to happen as I start to restrict this is the flow is going to go down. If this is an automatic valve, it will open up to compensate because that's that automatic job. So I'll do it for a little bit, but there's going to be a point where it cannot overcome because what is available is going to be less than what's required. I'm creating that imbalance the other way, right? Okay. Flow started to come down, opened up, went back to 45 gallons per minute. Life's good. I'm going to continue to pitch off or restrict the inlet line. This is going to go down. What's going on with these three? That went down, strike one. That went down, got that one. What happened over here? Down. It went down. All right. Why did this one go down? Remember, we created a imbalance the wrong way. We didn't have enough. It created, where did the bubbles come from? the vacuum. Remember how we talked about it up in the classroom? The bubbles appear, the balance of power went the wrong way, and it created a cavitation effect. So it produced a vacuum effect on the inlet. The discharge pressure went down. Why?
Flow.
No flow, no resistance, nothing there, so it went down. Does that make sense? What happened over here? Everybody thought that the amps would go up. The power would go up.
They're not working as hard.
It's not working as hard. There's no head, nothing to pump against it, no resistance, so it went down. It works less. All right? Okay. Was the pump the problem? No, but we always point the finger to the pump, don't we? Does it make a difference when we look at the pump as part of a system, right? Okay. Now, I'm going to create a problem on the discharge side. Okay? What's going to happen to this gauge? Is it going to go up, down, or stay the same? Chip, you seem to be the only one that give me answers.
We'll go up.
Going to go up. What's going to happen to this one? Everybody's looking at me like that. Give me an answer. Don't shake your head. Up, down, stay the same. Up. All right. Up. What's going to happen here? Up, down, stay the same.
Go
Up.
Go up.
Well, we'll keep it there. Up, up, up. Is that your final answer? Dum, dum, dum. Here we go. Going to pinch it off, which is not what we want to do. It's bad for a system if we pinch it off for a long time, but we can pinch it off for a short period of time. First thing you're going to see is that the flow go down. That stayed the same.
Yeah.
This did what?
Went up.
Went up to about 16, 17 pounds,
The amps.
and this went down. All right, let's get the system in proper imbalance, right? Why did this not go up? Some of you thought this would go up. Why? This is the inlet. The only way it can go up is if you start pushing back out this way. If that's the inlet, it's not going to push back out, so it stayed the same. This went up. Why? Because we pinched off, we have a smaller area, it's going to build up a little bit of pressure. Okay, it built up a little bit of pressure because what the area we had at once before, we've reduced it so the pressure that was in there, the pump spinning, it increases pressure slightly. Went down again. Why did it go down the first time? No resistance, nothing pushing up. Okay? There was no head, no flow, no resistance against it to make it work harder or make it work less. It actually worked easier, worked less. So the amps went down. Now we did a scenario where the discharge is restricted and a scenario where the inlet is restricted. Which one of these three bits of information was consistent? This told us down both times. Is that a very reliable source? No. This stayed the same. This one is. So when we want to gauge on our system, we want to gauge it's accurate on our discharge because it tells us where the problem is. And both scenarios that we just went through, the problem is not the pump. It is in the system. So if we have the pressure goes down, it's in what side of the system? What side of the pump? The inlet. Goes up, it's what side of the pump?
Discharge.
Discharge. All right, now, if you're out there walking around and you hear this, cavitation, what that means is this is no longer up here, it's down here. How can I return the balance of power back to the net positive section available? Huh? I want to reduce what's required. How can I do that? How many times do we shut the system off when all we have to do is close the discharge valve? What we did is we restored that imbalance of power. Because when we have cavitation, what's required is more than what's available. So if we lessen what's required, we restore the balance of in power in our system. Does that make sense? We don't shut down our system. Where do we find our problem when it's cavitating? Cavitation will always come on what side of the pump? The inlet side of the pump. We didn't shut our system down. We get on a squawk box or a radio and say, hey, close the discharge valve. Where's it at? 30%? Take it down to 20. Clean the basket strainer. Make sure the filters are clean. Make sure the valves are open 100%. A valve might have partially shut. All right? All right, what we're going to do now is we're going to go with a strobe light. And you are going to have to come up here for this once I get it set, because we'll turn the camera off and do it here in a minute. So, gather around. No, really, come on. Pretty much stop that impeller. Can everybody see it? You can come around this side. Okay, cavitation, what we're going to do is we're going to cut it off here. Here's what happens inside of that pump. That impeller is spinning counterclockwise. It actually increases in RPMs. There's cavitation. Remember I showed you up in the classroom, 1 row bubbles? Many bubbles. It's beating the living crap out of that impeller. Okay? Now, what's that impeller attached to? Did everybody see that? Did you see it? Okay. What is the impeller attached to? The shaft. What's the shaft attached to? Motor. What's in between the motor and the impeller? That mechanical seal. So when we're beating this impeller, it's just sitting there shaking the crap out of it. Okay? It's destroying the seal. Now, let's go out here and I'll show you what else it's destroying. That impeller was brought to me from MPW. Okay? This impeller, the damage for this impeller, these holes in it that goes into your process is caused by cavitation. Because it's located on that side of the impeller at the end of it, there's 3 types of cavitation. This one is low circulation or low pressure cavitation. Okay? This come out of a sump. 9 months later, this one was brought to me out of the same pump. Did we learn anything? I mean, look at that. That's pretty well damaged, isn't it? Okay, now this is another one of those sound bites. You got to pay attention. You have this pump. I'm going to come over here. I'm sorry. And we're all intelligent adults here, right? And we know that the level of this sump is here. And my line coming out of it is here. But what caused that damage? The level was right here. Now every one of us can say, my discharge line is lower than the level of my fluid. This pump sounded like this. Just cycling through. Have you ever heard a pump do that? What's going on inside of that system? What happens inside this pump when fluid is being drained out of here? There's a vortex, a tornado effect in there, right? So what's going on is when the pump starts to chew up and do that, that's sucking air in because that vortex opens up and it sucks air in at the bottom of the vortex, and then it collapses on itself and it gets quiet. And then it builds that vortex up. Okay? Now that can be prevented. 3 ways that can be prevented. One is operators turn it off before it gets that low. You don't turn your sump on and leave it running. Okay? Watch your equipment. A second way is, usually on some of these systems there's a level transmitter on them, right? Well, let's adjust the level transmitter up. Maybe 5% of the tank. And then we don't ruin that impeller. A third way is to go in here and put a vortex inhibitor, which is like a baffle in here or a little plate to prevent that vortex from forming. So we can stop that. But we have a prime example. We didn't do a very good job here. Okay? So, does that sound like something that's happened in your area? Remember that balance of in power? The imbalance? We have to maintain that imbalance where this is greater than what's required. Alright? Okay. Let's look at this one. Look at the top of this impeller compared to the top of this impeller. This is not cavitation damage. Okay? This is cavitation damage. If we look at this close enough, we will see inside of one of the vents, or the vanes, see it? Is a piece of polymer. See it in there? That one piece of polymer on that vane created an imbalance that actually changed the flow and ate away that impeller. Didn't happen overnight. This was a long time. Remember we talked about what happens inside of a pump? We have to maintain the balance inside. The system, we have to maintain an imbalance. This was imbalanced inside the pump. Okay? Here's another impeller. This is the inlet. Look what junk's in there. Do you think that affected the flow rate in this pump? Do you think you as an operator would see that the flow is restricted or diminished? I would hope. Don't you take notes and charts and stuff, what the flow rate is? And when you see one go down, this could be another reason why your flow goes down. All right? This also not only had junk in it, look at the cavitation damage on it. Low pressure recirculation cavitation damage. Not only did it damage this impeller, it also damaged the face or the back plate. Look here. When we make imperfections on this, remember the clearance I talked about earlier? 18 thousandths of an inch? It's going to affect the flow rate, the capacity, and the effectiveness of the pump. Here is the back plate of a system. Now here's what happened on this one. They had the same system and it was shut down for a year. And then they put another fluid in it and started using it. And after about 5 hours, the pump crapped itself. And they couldn't figure out why. Remember earlier we talked about specific gravity? Specific gravity helps us maintain that imbalance. They went to a higher or a lower specific gravity. The pump didn't pump it up so high because it had less head capacity. It ate the pump up. It just sat there and turned it up and just cavitation destroyed it. All right? Questions? Nope. All right, let's look at one more thing here. If you have, there's a training pump up at the Career Center here locally, that they have a small little needle valve in the inlet line, and they pull the needle valve out, and you can see little air bubbles going in and hitting the impeller. And you can hear the cavitation. It doesn't take all that bubbles, but a single row of bubbles that will change the flow. It'll change the way it sounds. When that system is running, it is sucking in that air into the system. It's not wet down here. You don't know it's leaking. Have you ever had a system when you shut it down, it gets wet down here below it? You ever notice that when it runs, it's dry? But when it's idle, the insulation or underneath the floor under the piping might become wet. Not a big leak, but it becomes wet. That's when you tell somebody, you know, I think that thing, we got a cavitation problem, we can't figure out where it's coming from. I think we got a hole right here because it's always wet. When the pump is running, this is inlet. It's sucking in here, okay? It's drawing that in, that fluid in. It's also drawing that air in. So it's not going to blow water out. Does that make sense? So when this line has water in it, the pump is not running. That water's just going to stay here and drip out and seep out. So that's something to pay attention for when you all look at your system when it's idle. Somebody said they had a problem starting their pump, and it cavitated when they started. And they know they flooded it, they purged it, they primed it, but it always cavitates. What do you think is something they can do to stop the cavitation on the initial startup of a pump? If you're starting up and you have cavitation, where's your balance of in power? It's to the pump, right? So how can we make what's required less on a startup? Close the discharge. So you shut the discharge completely off and crack it open, prime the pump, turn the pump on, and after it starts running, then open the valve. You control that balance of in power, right? And then we were talking, he said, well, there's a nitrogen blanket on my tank that I'm coming off of. I said, how many pounds of nitrogen do you have on it? He says, about 8 to 10. I said, take it down to about 1. If you have a nitrogen purge on your feed tank, it could give you cavitation on a system that should be working because you're putting pressure in here on the inlet side. Inside of the pump is balanced. On the two sides of the pump system, it's an imbalance. Now, does that help you understand how come a pump does what it does? Any questions? Make sense? All right. Let's. Yeah.
The incident in Zytel with the autoclave, when the seals got hot, could you demonstrate that?
Demonstrate that.
The temperature on the seals?
Okay. What's the temperature here? Come up here and look at it.
6.5.
Okay. Now, I'm deadheading it. What's it doing? Getting colder?
Hotter.
Getting hotter, isn't it? What's it now?
38.3.
2 degrees in about what, 10 seconds? I'm not going to tear my pump up. Why is it getting hotter? It's sitting there circulating. It's just rotating around that impeller. That impeller is friction. The water that does not flush through here to help cool it, so it stays the same water, rotating in the same place. It's going to get hotter. The longer you keep it still, the quicker it gets hotter, and then we have the problem, right? Make sense? Okay. Now, here's an example of a semi-open impeller. Now, the open impeller and the semi-open impeller, we adjust the clearance not on the back of it to that back plate. We adjust it up here into the volute. What do you think happened? Because these were a matched pair. See how I scratched that up? See how imperfect that is as compared to this one? Do you think this thing made a sound? Metal on metal. Remember we talked about using 5 senses? No, I didn't talk about using 5. I talked about 4. Okay? This would actually make a sound, if you heard it, would probably hurt your ears. And even if you're in a noisy area, you ought to be able to tell this is screaming like a banshee engine. Right? Metal on metal. Now eventually it will stop because it'll wear all that off, but how much metal, where does this metal go to when it comes off an impeller? In your process. Okay? And that's not a good thing. Questions? Go upstairs, start to fill out your evaluations in.